we finally get to bring everything together you've learned. We've talked about temperature, solar energy, moisture, clouds, precipitation, stability, wind, pressure. We're going to bring it all together in the atmospheric planetary circulation. Everything we have talked about works together to provide what we need to understand this circulation. So, what are some of the features of this wonderful circulation? Well, think about it. If you have an idealized circulation and you had the hot side with direct sunlight and a cold side with no sunlight, and the Earth didn't rotate, we know that the cold side would get hot, and where the most direct sunlight hit, it would be the hottest in the tropics. So that would be where your rising motion occurs. Sinking motion would be on the opposite side of the globe, and you would just get these big circulation cells that would work from that aspect. But Earth rotates, so guess what? Wind shifts to the right, and we wind up with all kinds of circulation patterns within the globe. So basically, you get a low pressure that's near the equator. That rising motion, again, is still there. You get high pressure around 30 degrees north. You get low pressure about 60 degrees north. And if you look at the basics on the weather map, if you were to average everything out over time, this is really what does occur. You wind up with lower pressure down by the equator, where the intertropical convergence zone flows. High pressure is right across 30 degree north, and there's a series of lows across 60 degree norths. So it works, and you can actually see this in the wintertime, in the summertime, depending on January to winter. Big high here, right across. Lows up here to the north. In the summertime, those highs shift a little bit to the south, and so does the low path. Lows stay up further north. They kind of spread out. Now, these are the subtropical highs. One of the interesting things is, depending on which side of the high you're on, as to what kind of weather you have. Think about this. We live mostly on the east coast of the U.S. So the subtropical high cuts across the Atlantic at 30 degrees north. So if you live in Charleston, South Carolina, you're on the western flank of that east high. What do you get there? You get a lot of rising motion around it, a lot of moisture coming in from the ocean. And we think about the flow pattern being clockwise around it, you get a southerly fetch. What's happening on the other side of the globe? Over in the Saharas, we got a desert. That's because you're getting the warming, you're lowering pressures. Winds are coming out of the north a little bit there. And the same exact thing happens on the west coast of the United States. They're on the cooler side. So you can see these highs have a huge influence on climate around the world. There's a polar vortex up by the poles, circumpolar vortex. Very cold in the winter times and summertime even, but in the winter especially. And you get it at the North and South Pole. And in the mid-latitudes, you get this wavy pattern of winds flowing across from west to east. The tropopause really fluctuates. You think about it over the tropics. We know it expands the air when it gets warm. So it's pretty high up. Mid-latitudes, the tropopause is kind of up and down and all over the place because of these fronts shifting through here. Go up to the north, polar tropopause, fairly low, down close. We talk about trade winds that develop around these super large subtropical high pressure systems. And the tropical convergence zone follows the sun. So why in the summertime would it be so much further north than in the wintertime? Well, you got land. Remember, the oceans don't heat as much as land does. So that means it moves much less over the water, while over land it's going to move a lot more because the land heats a lot more in the summertime. And some features of this, we just talked about that high and how they are. Look at San Diego, almost no precip. on that very dry side. Look at Charleston. Lots of moisture. These highs are so permanently there that they actually create circulations within the ocean. We have what they call the North Pacific Gyre, North Atlantic Gyre. And guess what? If you look at it, the southerly flow here, that's the Gulf Stream. It comes out of Florida and up. All that on the western side of that North Atlantic Gyre. Notice on the other side, it comes to that way. It goes downward. It's colder over to England and all. But some of that warm air from the Gulf Stream does get transported up into the mid-northern Atlantic. Look on the west coast. It's coming out of the north, coming southward here. So that's why the west coast has cooler oceans, because they're getting a north fetch to the ocean. Monsoons, because of this monstrous meridional circulations we see here, there's a shift that takes place depending on where the intertropical convergence zone. We saw how it moved. And look at the shift in the wind direction with that caves with that. One part of the year, summer, is very wet, lots of moisture coming in. Winter, that is, ITC drops south of it. Winds come out of the north, very dry and fairly cold. So these are monsoons that set in and last for days. We actually have a North America monsoon. In the summertime, sun heats the ground in the northern part of Mexico. There's very high plateau here. Not a lot of forest or anything in that area. So it heats very well. It gets very hot, fairly high up in the atmosphere. You get low pressure at the surface. But one of the interesting things with low pressure at the surface, be created by heating, is that above it, eventually you get high pressure. So you wind up with high pressure right over that area as well. And with the low pressure there, you're pulling in moisture from both the Atlantic and tropical Gulf of Mexico and Southern Pacific. And all of that moisture gets fed in, causing clouds and thunderstorms there. One of the interesting things, too, is when you look at a long wave and look at the wavy pattern you see at 500 millibars, you really define 2 to 5 what they call Rossby waves in that big, long pattern. So we'll take a look at some of that here in a minute and see if we can spot these. But you can see here the zonal flow, the pattern is fairly uniform. There's a little dip, but it's back across. A lot of winters we get that kind of a pattern. And then other winters we get this, where it dips way down. Think about it. If you're dipping that far down, you're pulling a lot of warm air north and a lot of cold air south. So you're creating tremendous temperature contrast with that kind of a pattern. With this one, you get very weak, very small temperature contrast. Usually the atmosphere is somewhere between two of these, but sometimes it can get locked into one or the other. Think about it. This one's going to have pretty fast west to east flow. This one's going to be pretty doggone slow, moving everything west to east. So that's another aspect of these big patterns. There's blocking patterns that set up, especially when they get meridional like that, they can really block. And you can get cold air locked into some areas and warm air locked into some. This was an example of a blocking pattern that's set up during the spring, created tremendous rainfall in the Midwest in 1993 and caused a lot of very heavy flooding out in there because it was locked in from March to May, never changed. So the polar front is basically a very narrow transition zone between cold and warm air masses. It occurs somewhere approximately around 60 degrees north. And we know that cold air is denser than warm air, so the pressure drops very quickly right along that frontal surface. And what that creates is a pressure gradient. Low pressure to the north, high pressure to the south. Coriolis force starts acting on it. And what you wind up with is winds from west to east. Right to the north of those stronger winds are going to be that low and that polar air mass. To the south are going to be warmer air. So we can see that with summertime, jet streaks usually run pretty far to the north. Wintertime, they go much further south, sometimes all the way down across Florida. And there are short waves that ripple through these things, just little areas of actually enhanced winds. Jet streaks have a little bit more intensity to them. And when they do that, what you find up with is that these influence convergence and divergence aloft. And when they do that, they help to develop lows at the surface. So you can see here, and we're going to get into more of this next week, but if you have convergence aloft, you wind up pushing the air down. You wind up with a big high down below it. You have divergence at the bottom then. The opposite occurs. And notice that this is where the lows form. Usually out ahead of these little shortwave troughs. Left front quadrant, right rear quadrant of a jet streak are where divergence occurs. And they're areas where you look for extratropical cyclone development. Now we're going to talk about El Nino and La Nina. Guess what? We're going into La Nina this year. And we can see here they do oscillate over the years. This is every few years we get either an El Nino or a La Nina. Another part of this is also the Ekman spiral. Water along the coast gets turned to the right. Say it's coming up from the south. And I've noticed this in the Outer Banks, where you get water gradually turning to the right as it's being transported to the north, and further until it circulates all the way around down the lower levels and comes back into the shore, pushing the low water up to the top and cooling mechanism to cool the upper water. And I have seen this off of Duck, North Carolina at times where one day the water temperature is 82, the next day it's 55. I'll tell you, the swimmers that went in that water that day really were shocked. They felt. El Nino's warm phase, air pressure falls more over the Pacific with the warmer motions. This is the, you can see El Nino, you get lots of thunderstorms over a lot of the Pacific. It changes the flow pattern over the whole globe, though. All those thunderstorms disrupt it. La Nina, cold. So only one area of the Pacific down near the equator gets it. And that can impact that area of thunderstorms. And it changes again. This big mass of thunderstorms changes the entire globe as far as the jet stream goes. North Atlantic oscillation. There's a positive index and a negative index. If the high pressure, positive index, you have stronger high pressure down here, weaker low pressure up here maybe, you wind up colder than normal in this section of the world. If you go the other way, you wind up warmer than normal, but you can get lots of thunderstorms, lots of snow events and stuff too with a negative NAO, because you wind up getting way more lows coming up the east coast of the United States. So yes, it does warm up some, but then it gets cold very quickly. So this pattern influences our winters more than anything else, more than La Nina, more than El Nino. And it's a pattern we have trouble predicting. Really, more than 2 weeks out, we have a lot of trouble predicting it. But when we get it right, and if we can forecast it, it can really show the influence of what our weather is going to be like for the next several weeks. So you can see it just changing with time. Another oscillation is an Arctic oscillation, which impacts our weather. Positive and negative phases of it, depending on how the cold the stratosphere is. There's a Pacific decadal oscillation as well, warm phase and cold phase. There's something called the Madden-Julian oscillation. Basically, it's a huge cluster of thunderstorms that develops somewhere typically around the tropical Indian Ocean, and it migrates eastward. It literally causes an impact into the stratosphere, and it messes up the jet stream tremendously. And if you track it around the globe, you can have one of these monster thunderstorm complexes, and they literally, the influence will travel around the globe in the next 30 to 60 days. And during that time, it will trigger cyclones, extratropical lows, major weather events around the globe. So there's something that's becoming more and more looked into to try to understand future weather. So with that, I just wanted to really show this is the current SSTs for El Nino and La Nina. And you can see here we keep getting colder and colder. And Nino 3.4 is where they look, and we're running about a degree colder than normal right now. They use 3-month average. So if you think, and it got to be at least a half a degree. So we've had July, we had August and September well below normal. So if we get October, which it looks like it will be, we're literally in a La Nina at that point. So this is looking at our jet stream right now as it goes across. Trying to look for Rossby waves is kind of fun. It's also kind of complicated. You look for the longer, bigger waves, I could say. Here is a big wave right here. So that would be one Rossby wave. Here is another big wave. So there will be two. I would argue that there's another wave just off the east coast, around the eastern part of the U.S. That's probably three, and there's another one over here, might be four. So there's basically four Rossby waves around the world at this time. Within those, here's one jet, here's another jet, here's another jet, here's a little jet, here's another one. Each one of these are short waves within this big long pattern of waves. So each one of these individuals has an impact on our weather. And finally, this is a little bit confusing, but I really want to look at just to see the global pattern right now. High pressure, 30 degrees north. Man, it looks like it pretty well around the globe. Lots and lots of low pressures right around 60 degrees north. One pretty strong one right here. Another one over in here. So again, the pattern, global pattern we've been looking at, talking about, is definitely here in reality.